Hello everyone, this is Chetana, a student of IIT Roorkee BTech TSAI second year. Today we're going to be discussing about a topic, spectral decomposition, which is from the course Applied Linear Algebra. Some pre-information that we require for this topic are symmetric matrices, orthogonal matrices, diagonal matrices, eigenvalues, and eigenvectors. A small description about each of them. Symmetric matrices are those which are symmetric about the diagonal. That is, if you take a matrix A and then transpose it, you'll be getting the same matrix back again. Orthogonal matrices are those which follow the simple condition of P transpose being equal to P inverse. And then diagonal matrices are those which have non-zero elements situated only along the diagonal. And rest of all non-diagonal elements are zero. And then eigenvectors. Let's say for an operator A, there exists a vector V such that when A operates on V, A just scales V by a factor of lambda. That is, it's not changing the direction of V. So then we could say that V is an eigenvector for a corresponding lambda. And then eigenvalue are those, let's say for an eigenvector V of A, when A operates on V, it just scales V by a factor of lambda. So this lambda is called eigenvalue. We can get lambda from solving this equation, that is det of A minus lambda I is equal to 0. Coming back to spectral decomposition, a square matrix A can be written in the form of P D P inverse, where P is the matrix whose columns are eigenvectors of A, and D is a diagonal matrix with diagonal elements as eigenvalues of A, given all eigenvectors of A are linearly independent. If A is symmetric, then we could choose the eigenvectors of A to be pairwise orthogonal with length 1. That is, P transpose is equal to P inverse. A can be further written as PD P transpose, P having its columns as eigenvectors of A. So V1 to Vn are eigenvectors of A, and then D having its diagonal elements as eigenvalues of A, lambda 1 to lambda n. And this is P transpose. So what is A exactly? A is basically a combination of transformations. That is, it could be stretching, compression, and then reflection along a certain axis. So A is a matrix that operates on another matrix, let's say X, to give a new transformed matrix, let's say B. In simple terms, a set of transformations to be applied to X is A. Note that each eigenvector points in the direction in which A stretches, compresses, or reflects by the corresponding ratio, the eigenvalue. What is meant by stretching and compressing? So let's consider an example where the green circle is the original circle and SV is the transformation applied to it. Any point on this green circle could be represented by the vector x equal to cos A 0 transpose, y equal to 0 sin A transpose. This is in the 2D plane where the standard bases are 1 0 transpose and 0 1 transpose. So the transformation that is being applied to it is this thing, SV. What this does basically is that it scales the x coordinate of the vector by 1.2 and then scales the y coordinate by 0.6. So as we can observe, it is being compressed along the y direction and it is being elongated along the x. So this is stretching and compressing. Understanding the equation A equal to PD P transpose. So what P exactly does is that it rotates the standard basis to align with eigenvectors of A. So let's say X is a vector with respect to the standard basis. Then P star X would be giving us the coordinates of X with respect to the new basis, which are the eigenvectors. And then D contains the stretching, compressing, reflecting parts of the transformation along the eigenvectors, which are now the new basis. And then P transpose just rotates the basis back to the standard basis. Have the code for spectral decomposition. It goes as follows. Generally, this algorithm uses power iterative method to find the eigenvalues and eigenvectors. And once we get the eigenvalues and eigenvectors, it is fairly easy to construct the decomposition. This happens at an order of n cube. That is the same as multiplying two matrices of order n cross n. I even decompose it. It is easier to perform operations on a basis which is standard than that which isn't. So therefore, we rotate the basis first and then perform operations on the basis, which are now the standard basis. Many complex problems could be solved efficiently on using the spectral decomposition of A. Examples being solving differential equations, solving linear equations, and simplifying matrix exponentiation and powers. Let's take an example. For given A and R, find A power R. A point to note is that multiplying two matrices of order n cross n will be done at a time complexity of order n cube, whereas that of multiplication of two diagonal matrices of the same order will be happening at an order of n, which is more efficient than multiplying two matrices which are non-diagonal. Therefore, let's take A power 50, where R is 50. A can be written as PDP transpose, assuming that A could be spectrally decomposed and it follows all the conditions of spectral decomposition. Then this could be further written as this. P transpose and P get cancelled because P transpose is the inverse of P. So it gets further transformed into this thing. And then this. D power 50 could be written in this way and then further into this way. You can check this by normal multiplication. Let's just say, let's take D square. Then you're going to multiply this with another of the same matrix. That is, you multiply this row with that column. Just lambda 1 gets multiplied with itself, the number of times whatever is there in the power. So therefore, d power 50 would be this. So let's discuss a little bit about the code part for multiplying two matrices of order n cross n. This is the code for multiplying two matrices of order n cross n. What this basically does is that it takes a row in the first matrix and a column in the second matrix, and then varies the column in the first matrix. That is essentially varying the row in the second matrix. So, which is the same as the formula. We multiply in a matrix that we have, we multiply the first row with the first column and then first row with the second column, and then so on, right? First row multiplied by the first column would be the element in the first position of the resultant matrix. So this is essentially that. Coming to the time complexity of this code, this and this will be of constant time complexity. Let's say this has a complexity of C1 and this of C2. Now this loop will be having a time, okay, for this part will be having a time complexity of n, and inside it, every case of I will be having a time complexity of j to be n again, and then k will be inside j, that will be n again. That is, for this whole part, the time complexity would be of order n cube. That is n into n into n. Therefore, for multiplying two matrices, each of order n cross n, we'll be getting a time complexity of n cube. Now let's discuss time complexity for two diagonal matrices. This is the code for multiplying two diagonal matrices. Now we know that apart from the diagonal elements, rest of all are zero. So we don't need to get into the multiplication of those elements. Therefore, this part is going to have a constant order, let's say C1, and then this statement is also going to have a constant order, which is actually 1, but let's just say this C2. Now, coming to the loop, this part is going to have a complexity of order n, because this will be happening n times. This will recursively happen n times. Therefore, this will be of order n. Then the whole complexity of this total code would be n plus some constant, that is an order of n. Take another example. For given A, solve the matrix exponential e power A. So we know that e power x is equal to 1 plus x squared by 2 factorial and so on. E power A in the same sense would be 1 plus a squared by 2 factorial plus so on. So calculating this again is not as efficient as doing this. Therefore, we write A as PDP transpose, then E power A would be transformed into this. Further, we could take P common and P transpose common. That will be leaving us with this equation. And furthermore, multiplying D with D, and all these terms would be written in this way. We could notice that every diagonal element of this part of the summation would be 1 plus lambda 1. Let's generalize this. We'll be getting 1 plus lambda I plus lambda I square by 2 factorial and so on as every diagonal element. That is, we will be getting e power a as this part. Each diagonal element would be exponential of that particular lambda eigenvalue. So this is way easier when compared to solving the complex equation in terms of a. The application of spectral decomposition is in inverting a matrix. So because inverting a diagonal matrix is very simple, the inverse of D would be simply a diagonal matrix with each element being the inverse of the element in that place of D. So let's say D is lambda 1, lambda 2, so on, lambda n as a diagonal elements. Then inverse of D would be 1 by lambda 1, 1 by lambda 2 as the diagonal elements, and rest of them as 0. So to prove this part, let's take A. That is P transpose. A inverse would be inverse of this part, that is further splitting it, we'll be getting and then this could be further written into one thing to note is that P transpose being P inverse, so P inverse of sorry, inverse of P inverse would be P again, and P inverse would be P transpose, and P inverse is this part. So A inverse is equal to P inverse P transpose. This is way more efficient to calculate than this part. So we can further write this decomposition as A being equal to summation of lambda I vi transpose, where vi transpose is the projection operator onto 1D span of eigenvector vi. A isn't a square matrix. Spectral decomposition can be further applied to A transpose A and A transpose, extending this topic to SVD and PCA. So this is some maths on how it is done, but we're not going to go further into it. So let's consider some applications: data compression and dimensionality reduction. In data science and machine learning, we come across a problem where we need to reduce the dimensions, but we need to retain the important information. How this can be done? It can be done using PCA. And then spectral decomposition is used to build up this concept of PCA. PCA identifies the principal components, eigenvectors of data, which can then be used for dimensionality reduction, sound reduction, and feature selection. And then another application, signal processing, breaking down signals into different frequency components. Then application and seismic data. Spectral decomposition is used in interpretation and analysis of 3D seismic data. It splits it into different components so that a further insight could be given on analysis of amplitude and frequency. And these are the differences that were used to make this PPT. That is the end of the PPT, and thank you for your attention.